Hello, can somebody confirm that you can hear me? Hello, can somebody confirm that you can hear me?
Yeah.
Thank you. All right, let's see. Make sure I'm not showing a grade book. That looks good. All right, we're good. All right, sharing my screen now. If you didn't notice, I graded Lab 2 last night, and I graded some other things over the weekend. So with Lab 2, I'm giving you not till this Saturday, but the Saturday after this Saturday to make corrections. I don't remember what else I graded, but that would have been over the weekend, and hopefully I don't think that was the lab. So you can't make corrections anyways. Any questions before we begin? All right, I'm not hearing any questions, so let's begin. That didn't give me a link to go to where we were last time. So today is April 20th, and we should be starting chapter 3. I don't think we're there yet. I think we're on chapter 2, but maybe we finished chapter 2 last night. Let me see what I've got. Oh, that does look like we finished chapter 2. So I asked you what molecules that we discussed have hydrogen bonds and give the molecule important properties. And nobody commented, so I want you guys to think about that. And then what would happen if these molecules were to lose their hydrogen bonds? If all the hydrogen bonds were to disappear in the world, what would happen to us? Okay, and that one I want to ask you a quiz question about, because I guess that's a little bit subjective and a little bit of an opinion, but you should know what molecules we discussed have hydrogen bonds. Boy, these are really dirty. All right, let's begin chapter 3. So here's my introductory slide covering chapter 3, observing microorganisms. The major goals and the rough outline are shown here. Know the terms, always know the terms for each chapter. 2, understand the sizes of organism and the properties of microscopes. Be able to understand the major differences between light microscopes and electron microscopes. 3, understand why staining improves resolution. So when we look at cells, they don't easily show up under the light microscope unless we stain them, and know why staining improves the resolution. And then you should know there's 3 types of stains: a simple stain, a differential stain, and special stains. And then lastly, know specifically the gram stain. Why is that not working? I can't raise it up higher. That's interesting. So understand the gram stain, its procedure, and the basis of its differential staining. Any questions about what we're going to be doing? I guess I didn't finish talking about the syllabus, so let me go on there. We're supposed to be covering chapter 3 and actually ending it today. I doubt we'll end it today, so we'll be falling a little bit behind schedule. There is no lab today. I will log in at the regular lab time, which is, I believe, 6:30. And I will be there for 15 minutes to answer questions. At 6:45, though, I will log off if there aren't further questions. So if you have a question, please log in the lab time from 6:30 to 6:45. And let's just minimize that and move on. So this slide is showing you the metric system. It's a unit of measurement. And in science, we use the metric system. In medicine, we use the metric system. You are expected to know the metric system, but let me blow this slide up. You really only need to know, well, most of these on the left. And then you should know the prefix meaning, so that when we talk about a kilometer, we can use a kilo, like with a gram, a kilogram, and a liter. So the meter is the measurement of distance or length. And when we're talking about weight or volume, we use grams. And wait a minute now. Weight or mass, I'm sorry, weight or mass, we use grams. And in volume or amount of liquid measurement, we use liters. And so we just switch the term gram, liter, and meter, depending on what we're measuring. But the prefix stays the same. So you should know a kilometer, and then obviously the basic unit, a meter. You should know a centimeter. You don't really need to know a decimeter. You should know a millimeter. You should know a micrometer. And probably you should know a nanometer. The nanometer is the size of a unit we measure when we're using an electron microscope. That's why you should know a nanometer. And of course, you should know the micrometer, because that's the size of the units that we measure under the light microscope. And then a ruler, do I have a ruler here someplace? Is the smallest unit of measurement on a ruler, assuming it has metric in English, which almost all rulers do, has a millimeter as the smallest unit on the ruler. I'll talk about that later. A centimeter on the ruler also. And then, of course, a meter, if it's a meter stick, it would have a meter. You do not need to know the metric conversion, that a meter is 39.37 inches. You don't need to convert between the English or US system and the metric system, but you do need to convert among the metric system. So you should know that a kilometer is 1,000 meters, and then a centimeter is 1/100th of a meter, or you have 100 centimeters to 1 meter. You should know that a millimeter is 1/1000th of a meter. A micrometer is 1/1,000,000th or 1 times 10 to the 6, meaning 1 times 10 to the exponent -6 meters. And then a micrometer is 1 billionth or 1 times 10 to the -9th meters. So you should be able to convert in metric units. You're expected to know, like I said, most of this column and most of this column. And I guess most of this column. And it's really easy converting in metric system because each unit is based on a unit of 10, like a meter is the basic unit. And let me see if I can remember. I think it's a decameter is 10 meters. You don't need to know the decameter. And then there's a hectometer, which is 10 decameters or 100 meters. And then there's a kilometer, which are 10 hectometers or 1,000 meters. And like I said, you don't need to know the decameters and the hectometers, but you should know the kilometer and the meter and the centimeter and the millimeter and the micrometer and the nanometer. Any questions about any of that? Okay, this map is showing you one reason why you need to learn the metric system. The map is colored, all the countries in the world that do not use the metric system. And all the other countries in the world which are not colored use the metric system. If you notice, there's only 3 countries in the world that do not use the metric system. And by the way, the United States is very slowly converting to use the metric system. That's why we have on our rulers the metric system in the English. And like on the signs, you go down the street, it'll have, or maybe on the cars, I don't remember which, it'll have both miles per hour and then kilometers per hour. So we are slowly converting to using the metric system. However, we're doing it very, very slowly because I think it was President Jefferson, the 3rd president of the United States, who passed the legislation through Congress saying that the United States would slowly convert to using the metric system. And we're going extremely slowly. So the English metric American system will be used for the foreseeable future. But everyone else in the world uses the metric system except for 2 other countries. Oh, you should also know the metric system for another reason, and I already mentioned that, and that is science and medicine use the metric system. All right, some typical sizes of microorganisms. Eukaryotic cells are about 10 times larger than prokaryotic cells. And this is a range, and obviously different authors have different ranges. The very smallest prokaryotic cell is about 0.4 micrometers. Most prokaryotic cells are between 1 and 2 micrometers, and about the largest prokaryotic cell reaches something like around 10 micrometers in length. Eukaryotic cell, it also depends on what size you're talking about. Most of them, I think, are around 10 to 20 or 30 micrometers. And we're talking like many blood cells, both white and red, are in this range. And then the upper size varies on eukaryotic cell. The largest eukaryotic cell that you guys have seen, and everybody's seen it, is the yolk of a turkey, not a turkey egg. Sorry, very few of you have seen the yolk of a turkey egg. The yolk of a chicken egg. That is the largest cell that everyone has seen. I had one student who did see the yolk of a turkey egg, but I've never had another student who did. I think she was from a farming family or something. And then, of course, the largest cell currently on the planet Earth is the yolk of the ostrich cell. And not many people have seen that. I've never even seen that on television. And obviously that cell is much bigger than 500 micrometers. But like I said, this is a range. Viruses are about 10 times smaller or even smaller than prokaryotic cells. The largest virus in its volume equals about the smallest prokaryotic cell. And the largest virus is about 0.44 micrometers in diameter. And the smallest virus is about 0.02 micrometers in its diameter. Now, you can take a volume, and many viruses are long and skinny, like the Ebola virus, and it's one of the longest viruses. It's actually smaller than 0.044 micrometers in diameter, but if you measure its length, it reaches about 1 micrometers long. Okay. All right. Any question about that? This slide is showing you the characteristic sizes of things. So humans, one of the bigger organisms, biggest thing you probably see that's alive. Chicken egg right there, which is less than a meter, but greater than a centimeter. Frog eggs, about the smallest thing we can see with our eyes. Eukaryotic cell, you need, at least for most eukaryotic cell, you need a microscope, light microscope to see them. Prokaryotic cells, smaller, so eukaryotic cells around this size. Most bacteria are around 1 to 2 micrometers. You need a light microscope to see them. Viruses, though, are smaller and they cannot be seen by a microscope, at least most viruses. Like I said, the largest viruses you could actually see with a light microscope, just barely. Come on, where's the mouse? So the smallest viruses are about there. And then we have things smaller than a virus, like a protein. These are very large molecules. And then we have small molecules smaller than a large molecule, such as water. And then we have atoms, which are the smallest thing we're going to really discuss in this class. To see the very small things, you need an electron microscope. You don't need to memorize this chart, but you should know the relative rank of the things I've talked about, and you don't need to know their sizes. Let me mention that this graph has an error. There it is right there. It has a micrometer right there, and that should be a millimeter right there. There's the micrometer. Any questions about any of that? If not, let's move on to the microscope. We're going to talk about the light microscope. And in the lab, we normally have a compound light microscope. A compound microscope is one that has 2 or more magnification lenses. We have the magnification lens in the objective lens and a magnification lens in the ocular lens. So both of these magnify the size of the specimen we view. The total magnification is the objective lens magnification times the ocular lens magnification. Most microscopes have 4 objective lenses. A 4x lens magnifies 4 times. A 10x lens magnifies 10x times. A 40x lens, and then the 100x lens. I normally call the objective lenses by their magnification, but we do have different names for them. The 4x lens is called the scanning objective lens. Come on. The 10x lens is called the low power objective lens. The 40x lens is called the high power objective lens. And the 100x lens is called the oil immersion lens. Note that the low power is not the lowest. and then the high power is not the highest. And that's kind of why I don't like using those terms. All right, any question about any of that? You should know most of the things identified in this picture. In this picture, it's even better. You should know. I think you should know everything in this picture. Okay, so you should know the ocular lens is here, the body tube here, the arm of the microscope also here, and then the objective lens here, the stage for putting the slide here. There's a stage clip, which we can barely see. Let's see if I can get that better. No. There, you can barely see the stage clip there. It holds the slide in the stage clip. The condenser, which is a lens, but it doesn't magnify the specimen. What the condenser does is it sends a cone of light from the lamp up to the specimen, which then goes up to the ocular, not the ocular, the objective lens. With the condenser is a diaphragm, and on this microscope, the iris diaphragm is below, come on, the condenser. On some microscopes, the iris diaphragm is above the condenser. The iris diaphragm opens and closes like a shutter, and it controls the size of the cone of light coming through the condenser. It's an important device for changing the amount of light that we're getting through the specimen. The illuminator, which is called the lamp or the light source, is where we get our light. We have the coarse focusing knob, which is the big one, and it lowers and raises the stage here greatly. The fine focusing knob here also lowers and raises the stage, but very slightly, very finely. And then, of course, the base of the microscope here. Any question about any of those parts? All right, so you should know those parts of the microscope and then what they do. Here we have a simple microscope, and it only has one lens that magnifies. So it is really nothing more than a super duper magnifying lens, because it only has one lens. This is a microscope that Antony van Leeuwenhoek made, and so that's why it's kind of simple. It was one of the early microscopes made, and that's how you viewed that. So you had your eye on this side, you put your specimen, you stuck it on the pen here, and then you viewed it under the lens. All right, the resolution of a microscope is the ability of the lens to distinguish 2 points. With our light microscopes, the best resolving power we can get is that we can see 2 points and distinguish them as 2 points if they are 0.2 micrometers apart from each other. So the resolution of the light microscope is 0.2 micrometers or greater. If we have something less than 0.2 micrometers, you cannot distinguish them as 2 separate points. So the resolution limit of a light microscope is 0.2 micrometers, and that's 200 nanometers. And that's true of all light microscopes because it is the resolution limit of white light. We're using white light to see a specimen, you can't resolve it any better than 0.2 micrometers due to the properties of light. Any questions about that? Sorry about that. The best compound microscope we have can magnify a specimen 2,000 times. Now, our microscopes in our lab only have an ocular lens of 10x and then an oil immersion lens of 100x. So the best microscopes we have in our lab measures 1,000 times. And obviously, we do not have the very best and most expensive microscopes, which can magnify 2,000 times. And they can magnify 2,000 times because they have an ocular lens of 20x. Any questions about any of that? You can't magnify greater than 2,000 times because the resolution limit of white light. If you magnify more than 2,000 times, it's empty resolution, meaning you get no benefit out of it because you cannot resolve anything smaller than 0.2 micrometers. So this would be two objects as seen under the light microscope, and they are exactly 200 nanometers or 0.2 micrometers apart. So that's the best resolution we can get. And there are the 2 points there actually shown. We can distinguish them as 2 points. You'll note right here that all of these points cannot be resolved because they're less than 200 nanometers apart. Any question about any of that? All right. When we're talking about light, you should also know that light refracts. Light, when it goes through one medium and then changes to another medium, has light refracting or bending. And that's why the pencil here looks bent. Okay, what's happening is the light is going through the water, and we see the pencil there. And then the light coming out of the water is refracted at the surface of the water and the air. And that's why the light bends right there, and that's why it looks like the pencil is bending. And right here, the light is only going through the air to get to our eye, and so the pencil isn't bent there. Any questions about that? So light bends whenever it's going through one medium, and then it switches to another medium. That we call the refraction of light. The refraction of light is actually very important for animals. Like when a bird sees a fish in the water, here's the actual position of the fish, but because of the refraction of light at the interface of the water and the air, it looks like the fish is higher up in the water. And so when the bird tries to catch this fish, it has to know that this is where the fish looks like it is, but in reality, it's really here. And animals do this instinctively, at least animals that are used to catching fish in the water, like birds. All right. The refraction of light is important in a microscope, and that is why we use oil with the oil immersion lens, because oil has the same refractive index as glass. And so when the light goes through the glass and then goes through the oil, the light is not refracted. Whereas the light coming through the glass and then going through the air, some of that light will be refracted. And some of that light will be refracted so hard, it will not it'll be refracted away from the objective lens. So this slide shows it better. This ray of light coming through the glass, going into the air, gets refracted so hard it's sent back into the glass. That one, the light is refracted hard enough that it will not be sent to the objective lens, and so that light is lost by the objective lens. That one is refracted, but it is not refracted enough. The objective lens still catches it. And then there's some rays which will not be refracted, and that will be obviously captured by the objective lens. So here's our specimen, by the way, and that's glass right here, at least the blue. If we use oil, then you'll note that this ray here, which was lost to the objective lens in the air, when we use oil, the light is not refracted, and so that ray will be captured by the objective lens. And that is why the use of oil helps improve the resolution of the light microscope. When we use oil, less light, actually no light, is refracted. So the objective lens captures more light, and that improves the resolution. And that's why we use oil with the oil immersion lens, meaning the 100x lens. If you don't use oil with the 100x lens, its magnification and resolution will be no better than the 40x lens. And the 40x lens is easier to use. We'll talk about that sometime later, either in this lecture or in the lab. I don't remember which, but we'll talk about that later. So if we don't use oil with the 100x lens, the resolution and magnification aren't any better than the 40x lens. So you should only use the 40x lens. Any question about any of that? And obviously, if you do use oil, then the magnification and resolution is improved over the 40x lens because of the decrease or the no refraction of light when you have oil in between the objective lens and the slide. By the way, I didn't mention it, but this light ray here will refract when it's coming out of the glass of the slide and entering the air. It will also refract again when it leaves the air and goes into the glass of the objective lens. All right. Bright field illumination is what a normal light microscope uses, such as all the light microscopes in our lab. What you see is an object which is lit up from the light beneath it, and then the background of the slide is also lit up from the light lamp below the specimen. What's happening is the light source is giving out light, and the rays coming through the condenser lens, going through the specimen, being captured by the objective lens. So bright field illumination is what we use in our microscopes in the lab. And it's called bright field because the specimen is bright, but then the background of the slide is even brighter. Any question on that? You will be tested on bright field illumination. On dark field illumination, you only need to know the concept, what it is. You don't need to know exactly how it works. In dark field illumination, we put a disc blocking the light coming from the lamp so that all of the light directly coming from the lamp going to the specimen is blocked by the disc. And that's why the glass background of the slide looks dark. Now the specimen is lit up, although it's darker than in bright field illumination. And what's happening here is we have some light which is sent from the lamp at an angle that normally would not be captured by the objective lens, but some of that light comes to the specimen and then is refracted, and it's refracted into the objective lens. Let me blow that up a little bit. Oop, from that one. So light that is refracted by the specimen is captured by the objective lens. So all the light directly coming from the lamp and then going through the specimen on the slide is blocked. Only the light sent out this way and then going through the specimen and being refracted into the objective lens is captured in dark field illumination. So all of the light in the background is blocked by the disc, but some of the light that's refracted by the specimen is captured by the objective lens. And that's why the specimen shows up on a dark background in dark field illumination. Any questions about any of that? All right. So that's the light microscope. Let's talk a little bit about the electron microscope. And here you're seeing an electron microscope, and you might notice it's a much bigger microscope than a light microscope. An electron microscope uses a beam of focused electrons instead of using light. The electrons, or the electron beam, is focused by an electromagnetic lens. It's not focused by like a glass lens. Electrons have a shorter wavelength than light, at least, well, actually, we're talking about visible light. And that allows us to have a higher resolution. So an electron microscope gives greater resolution. This allows the examination of things much smaller than we can see with a light microscope. For example, viruses, and then internal cell structures. There are two main types of electron microscopes. And yes, there are other types. We'll briefly mention them, but you don't need to know the other types of light microscope. You won't be quizzed on them, but you will be quizzed on the two main types: transmission electron microscopy, or transmission electron microscope, and then scanning electron microscope. What do you notice between these two pictures? What's different between them? You can see a difference right here. What are we looking at here? What are we looking at there? Come on, don't be shy. Nobody notices a difference? You should.
One looks more three-dimensional.
Yeah, you're seeing 3 dimensions with scanning electron microscopy. And in transmission electron microscope, we only have 2 dimensions. Transmission electron microscope is only viewing a plane through the specimen, whereas scanning electron microscopy is viewing a 3-dimensional object. So that's the first difference between the two. Thank you for stating that, by the way. I already mentioned that, so let's move on. Here we're looking at scanning electron microscopy, and you can see clearly this is in 3 dimensions. Scanning electron microscopy, I'm trying to remember what I'm supposed to be saying here, only views the surface of an object. We're only seeing the surface of the crystals here, and that's the surface of a cell here. Transmission electron microscopy views the inside of a specimen, or really it's only viewing one plane of the specimen. I suppose like if you had it perfectly on the surface of this thing, if the surface were like a square, you could see the surface, at least the top surface, not the side surface or the bottom surface. Like there's the bottom, there's the top, there's the sides. You'd only see one surface, but you could see the surface if you had it focused perfectly. With transmission electron microscopy, we can see inside a cell, but you only see in 2 dimensions, so it's only one plane that's viewable. And there is transmission electron microscopy. I think what we're looking at here is the membrane of a chlorophyll or chloroplast. Let me think about that. Membrane of the chloroplast. All right, there's a third type of electron microscopy. It uses a metal probe to scan the specimen, and this is called the scanning tunneling microscopy. You're not going to be tested on this. I'm just giving the name of it. It allows us to see very small things. It is a resolution of 1/100th of an atom, so you can go smaller than an atom with this one. And then the fourth type of electron microscopy is an atomic force electron microscopy. It uses a metal diamond probe inserting into the specimen, and it produces 3D images of the specimen. All right, here we're looking at 2 slides viewing cells here and then here. Which cells are easier to view? Cells on the right or the cells on the left? Or you guys really don't like to comment? It's pretty obvious. The only difference between these 2 slides is one of them has the cells stained. And I'll let you guys figure it out since you're not guessing here. And that's the only difference between these 2 slides. One of them has the cells stained. Staining doesn't do anything except increase the contrast between the background of the slide and the cell. So right here, this cell has very little contrast between this cell and the background. And then that cell there, let me blow that up. That cell there is very big contrast between the background of the slide and the cell. And that makes it easier to see the specimen. And that is all staining a cell does, increase the contrast between the specimen and the background of the slide, which for us is the glass slide. Any question about that? So with bright field microscopes, most microbes are essentially colorless and have little contrast with the slide or the medium that they're in. To see them, you therefore need to stain the specimen. Staining is applying color to the specimen or to the background of the slide to increase the visibility simply by increasing the contrast between the specimen and the background of the slide. To stain the cells, we usually prepare a smear before we begin the staining. And let me emphasize this again. A smear is something you do before you do the staining. So a bacterial smear is not a bacterial stain. Okay? And when you make a bacterial smear, you go through none of the steps of doing the staining process. Students always seem to get that wrong, so that's why I'm emphasizing it. A smear, all it is a thin film of solution of the microbes on a slide. Ideally, a bacterial smear should only be one layer of cells thick. Prior to the staining, we make a bacterial smear, and then usually we fix the bacteria on the slide by air drying the specimen and then heat fixing the bacteria or heat fixing the slide. That makes the bacteria stick to the glass. And that way they will not wash off by the staining procedure that follows making the bacterial smear. Bacteria, doing the heat fixing as well as the air drying helps a little, has the advantage that that tends to kill many bacterial species. Doesn't kill all, and certainly doesn't kill the endospores. Doesn't kill any endospore, but it does tend to kill most bacteria like E. coli. I'm trying to remember what my next part was to talk about, usually with, I don't even know what that goes to, so I'm not sure what that was going to be. Oh, well. Stains. Stains are, or dyes, those words are used interchangeably, are a salt consisting of a positive ion and a negative ion. The stain would be one ion or the other. So one of the ions is colored. We call that the chromophore. A basic dye is one where the chromophore is in the cation, the ion with the positive charge. An acidic dye is one where the chromophore is in the anion, the ion with the negative charge. And that's the only difference between a basic dye and an acidic dye, where the color is in the molecule or the salt. Bacteria have a slightly negative charge, so therefore a basic dye will stain the bacteria because the positive chromophore is attracted to the negatively charged cell. Most of the stains we have in microbiology are basic dyes like crystal violet, methylene blue, malachite green, and safranin. Acidic dyes have the negative charge being colored, and they do not stain the specimen, do not stain the cell, because a negative charge will be repulsed from a negatively charged cell. What a negative or acidic dye does is it stains the background of the slide, not the microbe. Some examples of a acidic dye are eosine, nigrosin, and an acid fuchsin. When we stain the background instead of the cell, it's called negative staining. So whenever we use an acidic dye, we usually call it a negative stain, as well as an acidic dye. A negative comes from the old cameras, which I think were Polaroids, and you'd have a film. And if you wanted to get more copies, you take in the negatives, and they were actually the negatives were only black and white, but they were the negative coloration of what you'd see in real life. So that something would be light, would be in the negative, something that would be dark. And then something that's dark in the negative will be light. Why it's called negative staining. And I realize that most of you probably have no idea what a negative was to those old films, but that's what they were and where the term comes from. All right, here we're seeing cells stain, and these are stained with a basic stain, and you can see that the cells pick up the majority of the stain, making big contrast with the background of the slide. Here we have a negative stain, and the cells are not stained, but the background is. So once again, we have high contrast between the cells and the background of the slide. And the cells are both easily viewable with a negative stain or a basic stain. Any questions about any of that? There are three main types of stains: a simple stain, a differential stain, and special stains. A simple stain is an aqueous or alcohol solution of one single dye. The primary purpose of a simple stain is simply to increase the contrast between the specimen and the background of the slide. You put the stain on for a certain length of time, usually a minute or two. It then is dumped off, usually washed off with gentle cold water. You then dry it, and then you can examine it. Sometimes we use a mordant. A mordant is not at least a normal stain. It is something that intensifies the stain of the first stain. In the Graham stain, we'll talk about iodine, which is used as a mordant in the Graham stain. The function of a mordant does not stain the cell exactly directly. It could be, well, we're not going to discuss it, so I'm not going to mention. But the function of the mordant is to increase the affinity between the stain and the specimen. It may coat the specimen to enhance it, and the Graham stain, the mordant binds to the stain, increasing the size of the staining molecule, which intensifies the, the stain, intensifies the contrast. Oh, that's the word I'm looking for. It makes the object stain more darkly, whatever that term is, okay? Enhancing the stain, making it more easily to be visible. Like with a flagella stain, we are just coating the flagella, and then we coat it again and again and again, and then it makes it more easy to see. With the Graham stain, like I said, the first dye gets in there, it's crystal violet, and then the Graham's iodine actually binds to the crystal violet, making it a larger molecule, and that makes it stain more intensely. That's the word I was looking for, intensity. A differential stain is one that reacts differently with different kinds of microbes. Therefore, if you use a differential stain, you can distinguish between two different types of microbes. A differential stain usually uses two dyes or more, but that is not required. You could use only one stain in a differential stain. The most commonly used differential stains, at least in microbiology, are the Graham stain and the acid-fast stain. So these are two differential stains that we'll talk about. The Graham stain was developed in 1884 by Hans Christian Graham. And you don't need to know the year, but whenever you use and spell out the Graham stain, that G should be capitalized because it's named after someone. Okay? It's named after Dr. Graham. And he used it to differentiate between a bacterial infection and then the patient's own cells. So in the Graham stain, the bacterial infection stained darkly, and then the patient's cells stain pinkish or lightly. Okay. Microbiologists started using the gram stain, and they realized that it separated bacteria into two very large groups. Those that stain purple in the gram stain, we call those gram positives, and those that stain pinkish or red in the gram stain, and those we call gram negative. Almost all bacteria can be separated into gram positive or gram negative cells by the gram stain. All right, this is the procedure of the gram stain, and I guess I'll just quickly go through it. You first make a bacterial smear on the glass slide, you let it air dry, and then heat fix. And then after that part, you begin the staining procedure. You first flood with crystal violet for 1 minute. You then wash the crystal violet off with cold water and be gentle about it. You then remove the water or just shake off the worst of the water, and then flood the slide with iodine. Iodine is a mordant. You apply it for 1 minute. You then wash off the iodine with cold water. You then rinse the slide with the decolorizing agent, and that's usually acetone and ethanol, although there are other decolorizing agents. Acetone and ethanol is the most common. Acid and ethanol is another possibility. And the third possibility is only ethanol alone. And in our lab, we don't really use that. But I think the video you watch will only be using ethanol. I usually apply the decolorizing agent for only around 5 seconds. So you do this very quickly. You then wash immediately. You have to wash immediately because if the decolorizing agent is left on the slide, there will be decolorizing agent on the cells, and it will pull out the crystal violet from a gram positive cell, and that's not supposed to happen. You then rinse with water. That should be, oh, it's wash immediately, sorry. And then that's with cold water. And then flood with safranin, the counter stain, for about 1 minute. Dump that off and then wash with cold water. Then blot the slide dry and examine it under the microscope. All right. Any questions about anything we've covered today? If not, I'm going to stop here, and I will be in the lab from 6:30 to 6:45 to answer any questions. After 6:45, if there are not any questions, I am going to log out.
Are you only doing lecture today until 6?
Oh, sorry. Hold it, you guys. I forgot this clock is not correct. So the lecture is going to continue. I got to change this clock and I got to take it in to do that. And as I explained, the reason why it's off is I took it in to get it corrected, and it was like 4 or 5 minutes slow, and they corrected it. And then about 24 hours later, or the next day I looked at it, I noticed that the clock itself had moved. I don't know why. Okay. And I can't adjust it because you need an administrative password. So let's continue a little bit, because it's only actually 6 o'clock. I thought it was 6:20, which is why I was ending. Thank you for correcting me. All right. Let me see, we need to go to slide 54. We're on slide 34. We don't need to go to exactly 6:20, but I will talk about a few of the slides. This slide is showing you the gram procedure that I talked about here. So let's discuss this slide. When you apply the crystal violet all cells will stain purple, both the gram-negative and the gram-positive. Because the primary stain, the crystal violet, will stain all cells. We then apply the iodine, and it is a mordant. It makes the cells a little darker and a little more purple. The crystal violet is a blue purple. After applying the iodine, there'll be a purple, more of a purple color, if you know what I mean. And it'll be a little darker staining too, because the iodine intensifies the crystal violet. And what it does is actually makes a complex with the crystal violet. And then that crystal violet iodine complex is a larger molecule. Why it intensifies the stain. We then apply the decolorizing step, and it is only applied for about 5 seconds. You will remove, if it's done correctly, you will remove the crystal violet iodine complex from the gram-negative cells. So they will appear clear. If it's done correctly, you will not remove the crystal violet iodine complex from the gram-positive cells. So they will appear purple. And then you apply the counterstain safranin, which will color the gram-negatively clear cells reddish or pinkish. And that's when we have the gram stain. Gram-negative cells are reddish or pinkish. Gram-positive cells are purple. Now, if you do not immediately remove the decolorizing agent from the cells, the decolorizing agent is on the gram-positive cells, and with time, it will remove the crystal violet iodine complex out of the gram-positive cells. So that's why you need to immediately wash with water to remove the decolorizing agent. Also, if you apply the decolorizing agent for too long, something over 5 seconds, then you will remove the crystal violet iodine complex from the gram-positive cells. Conversely, if you don't apply the decolorizing agent long enough, you will not remove all of the crystal violet from the gram-negative cells. So the decolorizing step is the tricky one. It has to be done for the right amount of time, and you really don't have much time to play with, meaning it has to be within a very narrow range. Any question about any of that? All right, if not, I think I will go ahead and end it here. And I will see you if you have questions at 6:30 in the lab. If you don't have questions, you don't need to show up. Oops, that's wrong.
Was there a plan to like change the times for the quizzes?
Oh, you were supposed to bring that up earlier so I could announce it. Can you bring that up at our next lecture?
Sure.
Okay, because some people have already logged off, so. All right, thank you.